Welcome back. Now I'm going to talk about the value of information. And in order to set the framework, recall that this is what we have already proved, that if I look at the loss, which is a fraction of agents who leave the market unmatched, so the minimum loss is 0 and the maximum loss is 1. This is the picture that we prove that the loss of the greedy is much more than the loss of the patient. In fact, the distance between the loss of the patient and 0 is much smaller than the distance between the loss of the patient and greedy. But for all of these results, I assume that we have access to information about agents who are about to depart, i.e. critical agents, exactly at the moment that they become critical. Now, a question you may ask is, what if we have more information? What if I observe agents who are about to depart far ahead of time? Or what if we have less information, i.e. I do not observe agents who are critical? Well, that's exactly what I'm going to do now. In fact, I'm going to do the latter because the former is not as important as the latter. For the former, I know that whatever more information you give me, I'm not going to do much better because patient is already doing very well. So whatever is going to happen by having more information is somewhere between patient and 0, and we characterize this exactly in the paper. So I refer you to the paper to see this more information by studying the algorithm that we call omniscient. But this one is actually the critical part. What if I do not observe critical agents? And that's the main theorem of this section, that without criticality information, if agents become critical and leave the market because I can't observe them, then the loss of the best possible algorithm, the solution of that Markov decision problem, cannot be better than 1 over 2d plus 1. And recall that greedy algorithm does not need information about critical agents because greedy algorithm immediately matches all agents and all critical agents perish. So greedy algorithm does not need that information about critical agents, and then I can bound the performance of the greedy algorithm from above because I've already bounded from below in the previous theorem. From above, I can show that the loss of the greedy algorithm is at most log 2 divided by d. And if you look at these two numbers, this one is roughly 0.65 divided by d, this one is roughly 0.5 divided by d. This tells me that greedy algorithm is actually very close to the optimum, to the best possible thing you can do if you do not have criticality information. In fact, without access to criticality information, this very greedy and naive algorithm that we designed, match agents to a random neighbor whenever they arrive, seems to be doing very, very close to the optimum. This immediately tells me that departure time information and waiting time are complements, and waiting are complements. If I do not have information about departure times, I do not want to wait because greedy is doing very well. And I want to wait only if I have departure time information. Why? Recall that the loss of the patient algorithm is upper bounded by e2 minus d over 2 divided by 2. As a result, if I have departure time information, then I want to wait in order to achieve exponentially small loss, while without that information I cannot achieve that very small loss, and the loss would be always linear. Now let me tell you some brief overview of how I'm bounding this optimum. I have been telling you about bounding the best possible thing we can do without knowing what is that thing, without telling you an idea of how this works. So now I'm going to spend a few minutes to tell you how I bound this optimum without knowing anything about how it exactly works. And this is the idea. I don't know what is the optimum, but I do know that whatever is the optimum, it's going to have some pool size stochastic process, and that pool size is going to have some expected value. So let me denote E opt zt. Let me use this notation to denote the expected value of the number of agents in the market under that optimum. I don't know what is that optimum, okay, just to be clear. But let me denote E opt zt to denote the expected value of the pool size under that algorithm. Now I'm gonna draw the following graph. As a function of this expected value, which can be anything from 0 to, m, very, very large numbers, I want to draw the perishing rate as a function of this in two different ways. The first way is very, very simple, which is the following. Because I do not observe critical agents, all critical agents perish. As a result, the perishing rate is exactly equal to the expected pool size. Why? Because the rate by which someone gets critical is equal to the pool size, the criticality rate. Each agent gets critical with rate 1, so the criticality rate is equal to the pool size, and because all critical agents perish, perishing rate is equal to the pool size. So from this perspective, I would like to decrease the pool size as much as possible, because if I increase the pool size, I'm increasing the perishing rate. On the other hand, I can do the following and calculate the fraction of agents who come to the market, do not have any acceptable transactions, do not meet anyone during their sojourn, so they do not have any acceptable transactions during their lifetime, and so those agents will leave the market unmatched. No matter what you do, independent of the algorithm, no matching algorithm can match an agent who has not had any acceptable transactions during their lifetime. This will provide me with a lower bound on the perishing rate. Okay, so this fraction of agents will perish for sure. Now there might be some other agents who perish, but that's something which gives me a lower bound for the perishing rate. And this fraction is definitely decreasing in this expected pool size. Why? Because if the expected pool size is very, very large, if it's infinity, then well, all agents are gonna find at least one acceptable transaction with probability very close to 1, so this fraction is very, very close to 0. And if expected pool size is very, very small, say it's 0, then none of the agents are gonna find any acceptable transactions. So this fraction is going to be very, very close to 1. As a result, this is a decreasing function of the pool size. Now the point is that from the perspective of this new calculation, I would like to increase the pool size as much as possible. From the perspective of the first calculation, I would like to decrease the pool size as much as possible. And if I could carefully choose the optimal pool size, if I could carefully tell you what is my ideal pool size, this point here would be my ideal bliss point. Why? Because if I move to the left of this point, the intersection of these two graphs, then this bound, the fraction of agents with no acceptable transactions, is going to kill me. If I move to the right, this bound is going to be troublesome, and the point that these two graphs intersect, it's the best possible pool size I can have. It's not necessarily the case that I can have an algorithm that achieves that pool size, but that's my bliss point. And if you write down the closed form expressions for these two equations as a function of pool size, you can see that this pool size is exactly m over 2d plus 1. As a result, if you calculate the loss, it would be equal to the perishing rate, the lower bound on the perishing rate, divided by the arrival rate, m, which is equal to 1 over 2d plus 1. As a result, the loss under no algorithm can be less than 1 over 2d plus 1.